So we used Coalesce in the previous video to force Spark to move all of the data onto a single partition, and it appeared then that that solved our problem with the ordering not appearing right when we used for each. So you will see many blog posts and Stack Overflow answers saying that, oh yes, you should always be calling Coalesce when you're doing sorts. Now that's really not correct, and I'm going to explain in this video why Coalesce was the wrong solution. What we're doing by coalescing here is we're just creating a new problem. Assuming that after doing this sort we want to do some further operations on this RDD, then I'm assuming that we're still in the realm of big data. In other words, this RDD is still going to be massive. Well, I hope you can see that by combining it all onto a single partition, therefore it's going to be on a single node, it's going to be on a single physical Java virtual machine, we're probably going to end up with an out of memory exception here. And of course we're not going to get any further benefits from Spark as we do further transformations on this data. Now I will admit, yes, if this were the last action you were performing, you'd done transformations and you'd got down to some small data, then yeah, okay, this would be this would kind of work. But I hope I'm not confusing you. It's the wrong solution because this was the wrong explanation. This is absolutely not what's going on in the RDD. We need a better understanding. I'll talk in a few moments about when you would use Coalesce, but it's not the right solution for here. So I need to give you then an explanation. If I run this again, I think we're going to see another random set of gobbledygook, definitely not sorted, or at least partially sorted. You see, we have 857 coming out on top this time, so it looks good. And if you run down, it is looking a lot better. 16, but then we drop to 1, and yeah, as you can see, still the answer is coming out incorrect. Now I'd like to prove to you that this was the wrong explanation. I can do that quite easily. There is a method on our RDD. So I'm working on the RDD here, this sorted RDD. There is a method on all RDDs, in fact, called getNum partitions. It does what it says on the tin. This will tell me how many partitions there are in this RDD. Now we've never specified this. We haven't configured Spark to use a certain number of partitions. We've never done that. So it's a bit of an open question. If I just print this out, there are partitions. I wonder what the answer to that's going to be. Actually, really, we don't, based on what we've learnt on the course so far, we don't have any information to tell us what the number of partitions is going to be. Let's scroll up to the top. And it turns out that for me at least, there are 2 partitions in this RDD. Just 2. And by the way, just looking again, yeah, the sort is all wrong. It's starting with 1s this time. And we've got a lot of 1s. And there's our 857 coming quite a long way down the list this time. It's clearly something of a mess. Now the way it determines how many partitions there are in the RDD is actually just based on the size of the input data. I think by default, if you're working with Hadoop HDFS, for example, it makes the size of each partition be the size of a HDFS block, which I think, I might be wrong on this, but it's something of the order of about 32 megabytes. So you actually need to have a lot of data. You need to be into the megabyte range before you will even see any partitions happening. Now we have 2, but I think that's just because there's a kind of a minimum number. We're working on tiny data is basically the explanation of why we only have 2 partitions. Put a massive file into this and you will get a lot more partitions appearing.
Now it depends on the run. I can see from the last run actually that I wouldn't be able to explain it very well. So I'm going to run again. The output we're getting is actually pretty random, but I want to show you somehow that there's no way that the partition explanation that we had here is correct, because we only have two partitions. So what we would expect to see is sort of two sorted blocks. So here we've got 857 running down to some ones. That ends there. And now you might think, well, here's just partition number 2 that we're seeing sorted. But no, we get down to, in fact, it turns into a real mess here. We get down to ones here, and then we've got a 2. So then another big block of 2s here, and then they're in a right mess. So really, this looks like, if the explanation was correct, there would be hundreds of partitions. So this is more evidence, really, that the explanation I just gave is not correct. That was the explanation I was given when I started working with Spark, and it just didn't fit. And the reason it didn't fit was that when you're working in Spark, in some ways, you do not need to worry about shuffling the data, or you don't even need to know about partitions for the results of the actions that you're performing to be correct. So in all cases, we should be getting correct sorting, regardless of whether Spark's working with one partition or 1,000 partitions or whatever. Now, a lot of Spark experts out there will be howling in anger at what I've just said there with this first statement. You do need to know. You do need to know about shuffling, and you do need to know about partitions. You only need to know about shuffles and partitions for performance. Now, that is very important. Don't get me wrong. We're going to be covering that in the last chapter on this course. There's no point doing this if you end up with terribly slow performing Spark jobs. You need to know about it, but not for correctness. It's never necessary to move the data around between partitions in order to get the correct answers. I think that's so important to understand. So what is the explanation then? We're seeing the wrong results on the console. Well, I'm going to argue actually we're not seeing the wrong results. We have simply misunderstood the contract of for each. So I can finally now cut to the chase. What's happening with for each is that the driver is sending the for each operation to each partition. And the contract of for each is that the function that you pass into for each is sent across to each partition in parallel, and that function will execute in parallel on each partition. Now, if we were deploying this to a real cluster, then potentially each of these partitions would be on different nodes, and simply what would be happening on each of those nodes is the print line would be executing on each node. In fact, on the driver, you wouldn't even see any output. Now, we're not on a cluster. We are just on a single machine. But we do, or at least my computer, and I'm guessing yours does as well, your computer will have multiple cores. And the default configuration of Spark is that for each core that you have in your processor, Java will be spinning off a thread. So what we're experiencing is our two partitions, because we just have two partitions in our system. There is a thread running print line on this partition in parallel with a thread running print line on this partition. So actually the answer is simply that for each is a bit weird, and you've got to be very careful of the results of running a for each. Going back to the output of my last run, this is what's happening. Thread 1 is running through partition number 1, and it starts doing its print line. And that's why we've been seeing these numbers going monotonically downwards until, in my case, we get to this one here. And what we're seeing is now thread 2 running the print line on the second partition. But for some reason, it only got a chance to do one output when the other thread interrupted and thread 1 has started running again. So we're seeing the output here of thread 1 all the way down to, it looks like here. And now thread 2 gets a chance. And it looks like this second partition, because we've got a lot more results with just the word count of 1. It looks like partition 2 is full of these ones. So thread 2 is now kicking in, and now thread 1. And I hope you can see now, all we're seeing is exactly the kind of output you see when you write a multi-threaded Java program. We're seeing the results of 2 threads competing for processing time, and they're simply interweaving with each other. So we're not seeing the wrong results, it's just that for each is a little bit weird. So to summarize that, when you use for each, be careful, it's going to execute the lambda on each partition in parallel. And in parallel will mean threading if you're on just a single machine like me, or it will mean the nodes are going to be executing that command on their own machine. So what's the correct answer? What should we have done? Well, really, it's just exactly what we did in the worked solution on the previous chapter. As I'm saying on the caption here, really any action other than for each will give you the right answers. So whatever the action, apart from for each, they will be implemented to give the correct results. Now that doesn't mean that the actions are going to perform well, and we need to think about performance. But in terms of correctness, any action will understand that the data is partitioned and that we will want the answers in the correct form. So for example, in the previous chapter, we used the take 10 method, which took the top 10 results. So the implementation of take, the implementations of these actions is actually quite complicated if you look at the source code. But very roughly, take 10 will know that the partitions are sorted, and it knows that it has to return the top 10 answers, but regardless of the partitioning. It won't just take 10 from any random partition. Now, I can't actually remember how they implement the take method behind the scenes. It will be correct. It will be the top 10 across all partitions. So to go back to the code, we don't need to print out the number of partitions anymore. So be very careful when you're using for each. You'll often not see the answers that you expect. Really what you need to do, if I delete that line, you need to perform some kind of an action, as we did in the worked example, where we did the take, and then that will give us, in this case it's a regular Java collection. Then we can loop through those results and we know those results are going to be correct. If I run this, this is just exactly as we had it before. I don't want you now to be worrying that maybe if we keep running this, eventually we'll get some randomly different data like we were experiencing a few moments ago. Just to reassure you, if I do a take, let's say 100,000 or some big number, I'm doing that just to prove the take knows that this RDD is sorted, and therefore it's basically iterating through those partitions and choosing the results correctly. Hope you're happy that we're definitely seeing a correct sorting there.